Okay, I think we'll get started. So this is the fourth lecture in this series on the paper that my students wrote. And we are, of course, trying to find a general formula for the partitioning of any integer into any number of any type of non-degenerate increasing set. And so we've laid down the groundwork now, and today we'll talk about the main theorem. We're gonna just go through an example so you can really get a feel for it. And that's kind of how you want to be able to understand this anyway, is to write out the different terms and kind of see the patterns, and that helps you internalize what's going on. So the key result is that we can now map this to a conjugacy class. So we can represent this in a succinct symbol Ci, and that's just sort of because of that isomorphism we showed last time. And then it turns out that the formula for the number of partitions, remember the representations are order matters, partition order doesn't matter. So the number of partitions is going to be 1 over m factorial. Where's this guy coming from? Well, this is coming from accounting for the order, and of course partitions are going to, permutations are going to give us, are related to finding the when order matters. So basically we're dividing by m factorial. So in kind of in a rough shot, we have accounted for all possible orderings. But in doing so, we have miscounted a little bit. And so we have to clean that up a little bit by taking the trivial irrep. So this really wouldn't need to be here because this is always 1, but I think it's nice to have it here to have some parallelism with the distinct partitions. So we'll take the trivial irrep, so always 1, times the size of the conjugacy class times the conjugacy class, and that will give us the generating function for the partitions of this. So it'll allow us to cast the partitions in terms of the generating function for the representations, but a much more elaborate formula is needed. And then what's really interesting is that if we simply change to the sign irrep, then we actually grab the distinct partitions as well. And so there's just a really small change in formula here, one where we are using the trivial irrep and one where we're using the sign irrep. Okay, well, let's work with the example of m equals 3. I think it's rich enough. It is rich enough to kind of see what's going on, and then you can, I think you'll easily be able to see, oh yeah, this is how this would work in a larger setting. Okay, so we can get the representations very quickly from the generating function itself. So the generating function gives us the representations for m equals 3 by just cubing it. And we see that when we cube it, we get 3 independent dummy variable or sums over this this sum of in the exponents here, right? And so if we were to write this out, we'd have S0, 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 0, 1, S0, 0, 2, countably infinite, but pretty, a lot of terms even for for the very first members of the set, because we have 3 up in there. So let's write that out, but let's collect those in special subsets of terms. So in green here, I'm pulling out all the terms where J1, J2, and J3 equal each other. So we're going to call these the full self terms. Right? And notice that, well, first of all, let's count them. There's going to be 3 factorial, right? But these are all the same. So we would have 3 factorial divided by 3 factorial, or 1 each. So there's only going to be 1 term that's 0, 0, 0, and 1 term that's 1, 1, 1, and so on. Well, this could be written as the sum of q to the 3 Sj, right? It would collapse to a single sum, And that would just be this guy. So we've seen that in previous lectures. So we can see that there, that there must be there's a hint here of a generating function of this form there. Now, let's look at the red bits. This is where we're going to have two of the same, right? So 0, 0, 1, 0, 0, 2, but not 0, 0, 0. That's already accounted for up here. And not 0, 1, 2. That's going to be not in this set here. Now, look what happens here. If we look at this guy, we're going to have 0, 0, 1, then we'll have 0, 1, 0, and we'll have 1, 0, 0. So we're going to have the permutations of 3 items, but when 2 are the same. So that's going to be 3 factorial over 2 factorial over 1 factorial. So that equals 3 each. Okay? And notice this is like the sum over 2, j1, j2, of q to the 2s plus q to the s, right? And so it is like this factor here, except we are not allowing for this to include when this is 0, because that's up in here, and that term would include that. Okay. So we'll refer to these guys as partial self terms. Partial self terms. Almost this, right? Except not when those are the same. And then let's look at the fully cross terms. So this is what everything is different. And of course, that is going to be this case, but we've already accounted for the terms that have j's equal to each other. So now it comes, now we're just simply counting now, and we're going to see what's going to happen here now. So if we just take this bit, that's going to give us 6 fully cross terms, right? Because this is just going to be 6 factorial, or 3 factorial. Oh yeah, here it is, right here. We have 6 of these. Then we have 3 of these, 3 each of those, and we have 1 of those in this set. So if we were to take this and then divide by the number of permutations, well, we have correctly accounted for the fully cross terms, because there's 6, right? 6 like this. Those orders matter. When we're doing a partition, the orders don't matter. So by dividing by 3 factorial, we've collapsed those representations that where it's just an order difference down into one partition. So it correctly accounts for that, but it undercounts the partial and full self terms, right? Because we're dividing by 6. We don't have 6 of these, right? So we're undercounting those. Okay, well, let's add a little bit to this. So we'll take this in steps. Let's add this now, okay? So we're going to only look at the partial cross terms, so not the full self terms. So in the partial cross terms, we have 3 each of those, right? And so when we divide by 6, we're going to get 2. So we're going to have to multiply by 3. That's where this is coming from. We're going to have to multiply by 3 in order to bring that up to 6, so that we have 6 divided by 6 to give us the proper counting of each of these partial self terms. Okay? So in doing this, we have now got, let's look what we have. Well, we have correctly accounted for the full cross terms. We have correctly accounted for the partial self terms. And now what about the self terms? Well, we've added this in here. So this is going to this, right? This is not the red. The red is this without j equals this. This is with j equals 1 and 2. So here, this includes fully self terms in here, as does this. So this has 1 fully self term. This has 1 times 3 or times 2 or 3 self terms. So we have a total of 4 self-terms, full self-terms accounting for. So in this bit right here, 0, 0, 0 would show up 4 times, right? But it's being divided by 6 and it needs to count once. So we have to finalize this by taking 2 times the full self-term set there. So that's how this comes about. This now accounts for everything. It has reduced all of the different types of representations down into their appropriate partitions. And that is indeed then the formula for the partitioning. Now, where are these coming from? Well, we can just say 1, 1, 1 out in front, right? So that's pretty easy. So that we can call that the characters for the trivial class. And then these are you can kind of think of these as the complement to these, right? In terms of that's not quite the right word, but how do we compensate for this undercounting? And we can do that by taking the size of the conjugacy class, right? The size of the conjugacy class. And so that's what's showing up here. That's these numbers here. Or here's a 1 and there's a 2. So it's a 1, 3, 2. And if we look at our table number 1 for m equals 3, we'll see that the conjugacy class size is 1, 3, and 2. The sign is 1, minus 1, 1, but right now we're using the trivial representation, so that is going to be 1, 1, 1. And then the correct psi is psi q3, psi q squared, psi q, and psi q, q3 like that. Okay. And so we can construct this final as being as coming from the table. So once we have this table, we can construct this. Now let's look at the distinct partitions, and that's going to be a little bit trickier, right? This formula looks a little strange because, for example, we're adding in some self-terms, and of course the self-terms should not be there because they are going to be definitely a repeat. So what we really need are the distinct full cross terms, and then we have to subtract off both of the partial self-terms and the full self-terms, because in the partial self-term and in the full self-term we're going to get repeats. Now, so we might think, oh, let's just subtract this and subtract that. But if we do that, then what's happening is we are accounting, we've got one term here, right? We're subtracting 3, right? So that gives us a minus 1, or minus 2, right? So one self-term comes from here, right? Just 1. Then 3 from here, because it's 3 times 1 coming from here. So that's 1 minus 3, that's minus 2. So we have to add 2 back in order to get 0. We want 0 self-terms. And that's where that's coming from. And it turns out that if we carefully look at the different conjugacy classes, then this guy is simply the sign of the number of the cycle type. And as long as we are subtracting the odd cycle types and adding the even cycle types, we're going to end up canceling out all of the self-terms and the partial self-terms. Those have to equal 0. And that leaves then just the distinct full cross terms that are contributing to the partitions. So we have taken the partitions and we've removed, by doing this, even though it's not both minuses, by doing this, we have removed the repeats. And so now we have the distinct partitions. For triangle numbers, this recovers the earlier work that we talked about in the introductory lecture, lecture 0, as to what motivated this, but it also just expands both in terms of this never says what set we're using, so it works for all sets of this type, and then this is just the case for m equals 3, but we can pull all of these data from the symmetric group, and the symmetric group, of course, is well studied, and this table can be built essentially arbitrarily high and very fast for even up to rather large numbers of m. Okay, so this kind of completes the main thrust of the paper. Hopefully you have kind of a sense for where things are. I think where I'm maybe still haven't convinced you yet might be why are these the conjugacy class size. So focus in on that. Maybe if you're still struggling to see that, maybe you're seeing it right away. And then also, like, why are these the sign characters? That's a little bit tricky, I think, to really understand. So you got to kind of think about that, work it out by hand. So I think if you work this out by hand I would suggest doing m equals 2, which is kind of trivial, but that really is helpful. And then m equals 3, like we've done here, redo that by hand. I think that will help you get a good sense of what's going on and kind of seeing naturally where these come from. All right, we will do, in the remaining part of the course, we will do some applications.